Okay, let's go ahead and get started here. So today we're going to model heat conduction through a large plane wall. And so what we have here is a large plane wall with a temperature of 200 degrees Celsius on one side and a temperature of 30 degrees Celsius on the other side. And if you recall, anytime you have a temperature gradient like this, where it's hot on one side and cold on the other, you'll have heat transfer through the wall. And so today I'll show you how to model this heat transfer and how to calculate things like the rate of heat transfer and the heat flux. So for this problem, we're given the thermal conductivity K equal to 20, and we're given T1 as 200 and T2 as 30 degrees Celsius. So I'll go ahead and open up console here, okay, and I'll click on the model wizard, and I'll click on 3D since this is going to be a 3D geometry. And this time we're going to model heat transfer. So the physics we're going to select is this heat transfer in solids, and I'll add that to the model. And click on study. And we're going to start with a stationary study or a steady state study. So COMSOL calls steady state as stationary. So I'll click on stationary and I'll press done. And if you recall, stationary means that it doesn't change with time, okay? Meaning it's steady state. All right, so I got my workspace set up here. And now I want to build that wall. So I'm going to right click on geometry and add a block. And let's make the wall 0.8 meters thick and 3 meters depth with 4 meter height. And click build selected, and there we go. We have our wall. Okay, now we will add some material properties. So I'm going to right click on materials, and this time I'm just going to click on new because I'm going to manually add the thermal conductivity of this wall. So if we come back here to the problem we're working on, we're given the thermal conductivity. We're not given the density of the wall, and we're not given the heat capacity of the wall either. But as it turns out, if we only want to model and calculate, if we only want to calculate the rate of heat transfer and heat flux, if you recall from Fourier's equation, okay, Fourier's law for calculating rate of heat conduction, the formula is the rate of heat conduction is equal to the thermal conductivity times the area times the temperature difference divided by the thickness, and the units are given in watts. And so you'll notice here you don't need the density to calculate the rate of heat conduction, nor do you need the specific heat capacity. Now, if you wanted to calculate something like the thermal diffusivity, okay, then you would need the density and you would need the specific heat capacity. But in this case, we're just going to model the rate of heat transfer and try to calculate the heat flux and the rate of heat transfer through the wall. So we don't need the density and the specific heat. So the problem we're working on here, we're given K, the thermal conductivity, as 20. So I'll go ahead and manually put in K here as 20, and I'll leave the density blank, and I'll leave the heat capacity blank as well. And notice that this property, this thermal conductivity, is being applied to this domain 1. There's only one domain here. That's this one here. Okay, so we've added the thermal conductivity. Now let's move on to adding some boundary conditions. So I'll right click on heat transfer, and I'm going to add a temperature. And on this side, if you recall, the temperature is going to be 200 degrees Celsius. So I'll put in here 200. And remember, COMSOL, the units for COMSOL have to be in brackets. So I'll do an open bracket. And for degrees Celsius, COMSOL, you write degrees Celsius as DEGC, capital C. Okay, and then close bracket. So that sets up the boundary condition on this one. Now we'll go ahead and set up the boundary condition on the other side. So I'll right click and I'll add temperature again. Notice it adds a second temperature, and I'm going to click and left click and drag, and I'm going to select this other side. Okay, and the temperature on this other side is 30 degrees Celsius. So I'll go ahead and put in 30 degrees Celsius. Okay, and so that set up my boundary conditions. I have my temperature on one side, temperature on the other, and I've given COMSOL the thermal conductivity, so it now has everything it needs to calculate the rate of heat transfer. So I'll go ahead and move on to the mesh and build the mesh. Mesh is built, and I'll go on to the study and compute the study. And notice the progress, green progress bar down here at the bottom. It just takes a few seconds to compute, and the default results are to plot the surface temperature in Kelvin, where white is hot and this dark red is cooler. And you can change the color scheme by clicking on surface here, and this color scheme right here is called thermal light, and you can change it to something that might make more sense, like this rainbow color scheme, okay, where red is hot and blue is colder. Okay, and that makes sense, a little more sense to me, so I'm going to keep on this color scheme, and I'm going to change the units here to degrees Celsius, since I was working in degrees Celsius. And notice if I click on this side of the wall, the temperature on that side of the wall is 200 degrees Celsius, and if I click on the other side, it should be 30, right? Because those were our boundary conditions. So if I click on that, I see that the temperature is 30. So that looks correct. But what we want to model and what we want to see is the rate of heat transfer and the heat flux. And just real quick, so just so you remember, the difference between the rate of heat transfer and heat flux is the rate of heat transfer is here just Q dot for conduction, and heat flux is if you divide it by the area. So if you divide it by area cancels out on the right hand of the equation, and you have rate of heat transfer divided by area, and that's what we call heat flux. Okay, and we give that as little q. So let me show you how to plot the heat flux first. So if we wanted to visualize the heat flux, I can right click on temperature here, and we can add a arrow surface. Okay, and here notice the default expression is heat flux. So that's the heat transfer. This is the variable that, of the heat flux in the x-axis. And so that's what I'm looking for. So I'll go ahead and press plot, and it'll plot the arrows, and you can see the rate of, see the direction of heat flux. And this is making sense because it's going from hot to cold, right? So the heat flux is going in that direction. Okay, but this just lets us visualize in terms of these arrow vectors the direction of heat flux. And but what if we wanted to actually calculate the heat flux? Well, to do that, we can right click on results and add a 3D plot group. Okay, then right click on this 3D plot group, and let's rename it to heat flux. Okay, and let's add in this 3D plot group a surface plot. So I'll right click and then click on surface. Okay, now the default is to plot the temperature, but I'm interested in plotting the heat flux. So I'm going to change the expression by clicking on this here, then expanding the heat transfer in solids, and I'll go here to domain fluxes and the conductive heat fluxes, and I want to plot the heat flux in the x direction. So I'll click on this one. I double clicked on that one, and it shows you the expression here as heat flux in the x direction. And notice the units. The units are what we expect. We expect the units to be watts per area or watts per meter squared. So that looks correct. And so I'll go ahead and click plot, and it'll plot the heat flux. Notice the heat flux is constant throughout because the temperature on one side of the wall is the same. It's uniform on that side of the wall, and the temperature on the other side of the wall is the same on that side of the wall as well. So that makes Q dot, or the rate of heat conduction, going through the wall. And if I click on anywhere in here in the green, it'll give me the heat flux, which is 4,250 watts per meter squared. So the units are displayed up here, and heat flux is given watts per meter squared, and the units are also displayed here. So that's given us the heat flux. Now recall, heat flux is little q. Okay, heat flux is little q, meaning it's rate of heat transfer, or big Q dot, divided by area. So what if I wanted to calculate big Q dot, or the rate of heat transfer? Well, I can do that by multiplying the heat flux times the area. That'll give me the rate of heat transfer. So let's do that. To do that, I will right click on heat flux, and I'm going to click on duplicate. So it's going to add that plot group here again, and I'm going to rename it. So I right click on it and press rename, and this is going to be rate of heat transfer. Okay, and here I'm going to expand the surface plot that we have where we're plotting the heat flux, but because we want rate of heat transfer, I'm gonna multiply this times the area. Okay, and the area, if you recall, is if I come back up here, the area is this face here that's 3 meters times 4 meters. So the area is 12 meters squared. So if I come back here to the rate of heat transfer and multiply this times the area, which is going to be 3 times 4, and add the units, and remember the units for this area that we're multiplying is meters squared. So I add meters squared, and then if I just click here in the units, it'll give me the updated units. So notice the units now changed from watts per meter squared to just watts, and that's what I'm expecting. That's what I'm looking for rate of heat transfer, just to have watts. And if I click on plot, it'll now give me and if I click on one of these inside this green box, it'll now give me the rate of heat transfer, which is this 51,000 watts. Okay, so that's how you can calculate rate of heat transfer, and you can calculate heat flux. Let me show you one last thing. If I come back to this arrow surface plot, you can change the size of the arrows here by changing the scale factor. So if I click on this scale factor and increase the bars here, you see the arrows get a little bit bigger. And again, the objective or the idea is to communicate, and to be able to communicate the results in a visual format to whoever your audience is. So sometimes you might want to increase the scale factor there so they can clearly see the direction of the rate of heat transfer through this wall.